Hello everyone. Today's lecture is about the Fourier series. The Fourier series is a mathematical technique that analyzes a signal, which is a periodic, to find the frequency content, something like this. And we want to know what are the frequencies present in this signal. So we will cover in this lecture the different representation for the Fourier series, trigonometric and exponential form. Also, we're going to talk about the Parseval's theorem, which is about energy and some application in system analysis of a periodic signal using the Fourier series technique. Before we start with the Fourier series, let's review sinusoidal function. For example, if I have this function, A in this case is the amplitude, and that will be here. And the frequency of the signal is 50 Hertz, so the period T is 1/50. So that's 20 millisecond. So that's the period from here to here. Now, if I take this signal and delay it by that amount of time, which is 2.5 millisecond, so what is this signal will equal? Well, I replace T by this quantity here. So I will get this signal. If I multiply the frequency omega, 2 pi 50 Hertz, time t, I get this. Omega time 2.5 millisecond, I get this, which is 45 degrees. So a delay of 2.5 millisecond is equivalent to 45 degree. That's, or a phase shift, 45. So if I plot this signal, it will look like this. So this is delayed 2.5 millisecond, and I plot it. Now the Fourier series, we said, it decomposes a periodic signal to a summation of sinusoidal function of different amplitude and different frequency. And this concept is not strange to us, because if you look at this example, if I give you 10,437 and I told you the basis function is 1,000, 100, or basis number 10 and 1. So I can represent the 10,437 or any number as a linear sum of these basis function. In this case, it will be there are 10 of the 1000, 4 of the 100, 3 of the 10, 7 of the 1. If I add this whole thing, I will get the 10,437. Also, we are familiar with vectors. So I can have in space 3 basis vector. If this is x, y, z, then this is this vector. And the y is this vector, and the z is this unit vector. And we call this the basis vector. So any vector in three-dimensional space can be represented as a linear sum of these basis vectors. So if I have this vector 2, 4, 5, it's 2 of this unit vector, 4 of the y unit vector, and 5 of the z unit vector. Fourier series is the same thing. You have any periodic signal. This periodic signal could be temperature, could be speech, could be anything. Fourier series will express this signal as a linear sum of sinusoidal functions of different frequencies and different amplitudes. So this signal here in MATLAB, you can generate it. It has a DC, which is this 1, plus a sinusoidal of frequency 1 and amplitude 1. Another sinusoidal of frequency 2 and amplitude 2. The amplitude could be anything. And a sine wave of frequency 1, amplitude 3, and so forth. If I add all these sinusoidal, I will get this periodic signal. And the Fourier series, that's what it does. If you have a periodic signal like this one, we can use the Fourier series technique to find its components. And that will tell us what are the frequency content. And there are many applications where you have a signal and you want to know what's the frequency content. So you can filter out certain frequency, amplify to manipulate the signal to your desire. And this is another periodic signal. And if we look at this signal, the period looks like from here to here. Then it starts repeating itself again, and so forth. So we can apply the Fourier series to find what are the frequency content in this signal. This signal could be just the sound of O or the vowel E. In the Fourier series, we can represent periodic signal x of t in 3 different forms. In this form, we call it the trigonometric form. Basically, any periodic signal can be represented as a DC, a linear sum of cosine function of different frequency component. F0 here is the fundamental frequency. That means the lowest frequency in the signal. Like if I go back to this signal, if this is the period T0, then the lowest frequency will be F0 1 over T0. So that will be a sinusoidal, something like this. That's the lowest. Then you will have the second harmonic like this, and the third harmonic, and so forth. So F0 is the fundamental frequency. When n is 1, that's the fundamental. When n is 2, 2F0, that's the second harmonic. When n is 3, 3F0, the third harmonic, and so forth. And every sinusoidal cosine has different amplitude, an, plus another sinusoidal sine wave, again with different harmonic or different frequencies and different amplitude. And we call this the trigonometric form. And we will find out how do we find A0, AN, BN, and so forth. And that's what's Fourier series technique. Also, we can express it in the compact trigonometric form. And this one, I can express the same periodic signal x of t as a linear sum of cosine function of different frequency or different harmonics. Each harmonic will have different amplitude Cn, and it will have different phase, and it has a DC. And we will see later, if we have this form, we can find this form. This is more common to use because you are dealing only with one sinusoidal cosine instead of here you are dealing with two. Now the complex exponential form is easy to calculate. So again, same signal x of t can be expressed as a linear sum of dn, which has a magnitude and phase, and this exponential. And this is different harmonic, nf0. Here n goes from minus infinity to infinity. And if I have this form, I can get this compact, and I also can get the trigonometric form. If I have this one, I can get here, I can get here. We cannot calculate this directly. So I either have this first or this to get the compact trigonometric form. Alright, so let's start with the trigonometric form. So we said x of t is a DC and a sinusoidal. The first challenge is to find the fundamental frequency, and that should not be difficult. You just look at the signal and see where it repeats itself. In this case, this is the period, the fundamental period T0, and F0 will be 1 over T0. So that's not difficult. But how do we find A0, AN, and BN? If we take the integral of each component over a full period, and this is the fundamental period, the integral of a sinusoidal over a full period will always give you 0, because if it's cosine like this and you integrate over a full period, the positive area will equal the negative area, you get 0. Same thing for the sine, same thing for here. You integrate a sine over a full period, integration is just a summation. The positive area equal negative area, and you get 0. So the only thing that will survive is these two terms. And the integral of A0 is a DC. The integral over a full period, you will get, this one will be A0 T0. And this is the integral of x of t. Divide by T0, both sides, that's what you will get, the DC. And that's how we find the DC. Basically, the DC present in any periodic signal, you take the area or the integral of the signal, the periodic signal, and you divide it by T0, averaging, and that will give you the DC. If the signal is centered here, it has some DC because the positive area more than the negative area, so you will get A0. But a signal like this, where the positive equal the negative, if you calculate this, A0 will be 0. Now let's see AN. To find AN, what we can do is, first we multiply every component here by cosine, if I want to find AN. By a cosine, this term, and multiply here by cosine, and then integrate. So I get x of t times cosine 2 pi f0 nt, and I integrate over a full period. Same thing here, A0 cosine 2 pi f0 nt. So I will do for all the terms. The integral of these over a full period will be 0 because of this cosine function. Sine times cosine integrate over a full period will also give you a 0 because the positive area, if I take a sine like this and then multiply it by a cosine like this, the positive area times positive, negative times negative, or positive times negative, you will get same area and you will end up with a 0. Or you can use trigonometric to break down this sine times cosine and integrate over a full period and you will get 0. Except this term. So this term actually it's like cosine 2 pi f0 nt times cosine 2 pi f0 mt. So when n equal m, you get the square. And when you integrate this, you will not get 0. What you will get is the integral of an, and cosine square, I can express it as half 1 plus cosine 2 pi f0 t dt. And again, the integral of this one is just half an, half here will come out, an dt plus the half integral an cosine 4 pi f0 t dt. And that's integral over a full period. Now the cosine integral over a full period, you will get 0 and you end up with this one. And this will be just half an t. And these terms will come here. Now, to find an, I can multiply this by 2. I can bring the 2 here and divide by t and the t here. And I find an. And that's this equation. So to find an, you just take the signal, the periodic signal, and multiply it by a cosine function, and you integrate, and you average it. T divided by t0 and time 2. Now let's see how do we find bn. Same technique. And I'm not going to go through it, but it's the same thing. How do you find bn? You multiply every component here by the sine term. So this will be x of t times sine 2 pi f0 nt, and you integrate. Same thing. You integrate, you multiply this by sine 2 pi. You integrate, you multiply this by sine. You integrate, you multiply this by sine. Only this will survive. This will go to 0. This will go to 0. And Pn will be this one. And that's how you find the Fourier series coefficient A0, An, Bn of the trigonometric Fourier series representation. So if we look at this example, let's say you have a signal f of t, and definitely it's periodic, and we need to find what are the Fourier series coefficients. That's A0, An, Bn. The first task is to find the fundamental frequency, f of 0. Let's find first the period. So the period, definitely the signal repeats itself every pi. So the period t0 is pi, and the fundamental frequency f of 0 is 1 over t0. So that is 1 over pi, and that is the fundamental frequency in hertz. If I want to find it in radians, it's 2 pi times f0, so that's 2 pi, 1 over pi, so that is 2 radians per second. Now to find the DC A0, it will be A0 1 over the period, 1 over pi, integral over a full period of the signal. In this case, signal is e minus t over 2 dt. So I will integrate over a full period from 0 to pi. And if you carry out this integral, you get this value. Now how to find An? An is the integral of the signal x of t or f of t times a cosine 2 pi f0 nt. And 2 pi f0, that's omega 0, which is 2. So that's cosine 2 nt, and that's this one. And to integrate this, it's going to involve u substitution and all these kinds of things. So it's going to take a long time to integrate it. And I'm sure you already did that in calculus many, many times. So for this course, I encourage you to use the integration table. Same thing, Bn. It's the signal x of t, which is e minus t over 2 times sine n, the fundamental. Omega 0 is 2, so that would be 2n. And again, use the table integral, and that will be your Bn. if I want to express f of t in this format, all I have to do is plug for a0 this value, plug for an is this value, plug for bn this value, and that's what you will get. And you do some algebraic gathering. Now, when you look at this sinusoidal, the first harmonic when n is 1, so that's 2 radians per second. The second harmonic when n is 2, that's 4. Third harmonic when n is 3, that's 6. So as the harmonic increase, the amplitude decrease. See, n1 over n squared. Same thing for an, divided by n squared. So as the harmonic increase, their strength, their amplitude. When I say an, that means this amplitude decrease. This amplitude, an and bn, will decrease as n increase. Now, when you calculate an and bn, there is some trick you can use to find an, bn without carrying a lot of integration. For example, if the signal is periodic like this, then definitely it will have only cosine function, because a cosine function is an even function. It won't have a sine function because sine function is an odd function. Odd, that means if I go 1 here and minus 1 here, this amplitude at 1 will be negative. This amplitude. So if that was like 0.8, this will be minus 0.8. Even the value of the function at positive t or negative t, as long as the magnitude is the same, the amplitude will be the same. So when you see a function like this and it is an even function, then you know it has only a cosine function. So that means it will have only an. It will have only this term. So bn will be 0 if the function is even. If the function is odd, then an will be 0. And bn will have some value if the function is odd. A function like this is an odd function. So it have only a sinusoidal function, it will have only bn. If the signal is centered like this around the horizontal axis, then the DC will be 0. Like this one, that's the DC 0. So you don't have to calculate A0. Now, for a periodic signal to have a Fourier series, the first thing, it can't go to infinity like a signal like this. Because if you carry out the integral, it will give you an infinite value. So then a periodic signal that goes to infinity will not have a Fourier series. Or also, and this is the Dirichlet conditions, also it cannot have too many discontinuity or too many maximum and minimum. So basically it can't go just like this or too many discontinuity in the signal. Most signals, they are continuous, few maximum, minimum, few discontinuity, and definitely don't go to infinity. Okay, now let's look at the compact trigonometric form. We will use this trigonometric identity. This trigonometric identity, basically C will be the square root of a squared plus b squared, and theta is minus tan inverse b divided by a. So we're going to use this trigonometric property, and if I have this trigonometric Fourier series, I can get easily the compact. So the C0 will be just the DC, the same. The Cn here will be the square root of an plus bn, which is this. And theta n here will be minus tan inverse bn divided by an. So we are using this, the trigonometric identity. This is more, since we are dealing with one sinusoidal, not cosine and sine, it's easy to grasp how these terms will add up to form any kind of signal. Like, for example, this square signal. How can I express it as a linear sum of sinusoidal? Well, first the C0, the DC, which is this one. Add to it the first harmonic. So this is the period is from here to here. So the first harmonic cosine or sine will be this. Then the second harmonic will be this, and the third, and so forth. So if I add the DC plus the first harmonic, that's what the signal will be. If I add the second harmonic, now it's gonna look like this. If I add the third harmonic here, if I add more harmonics, now see when you sum them up, they start looking like the square function here. And C0 will be this one. C1 cosine, when n is 1, that will be the first harmonic you add it to the DC. When n is 2, the second harmonic, and so forth. Now, what's the importance of the phase shift here, theta n? It's like a delay. For example, if I give you this signal, how are you gonna add cosine function that at 0 always 1, a cosine, no matter what is the frequencies of the signal? So how you can add all these 1, 1, 1 and you get a 0? Here is where the phase shift play a role. So you take a cosine and you phase shift it. So this cosine probably start here, you phase shift it to here, 0. And you phase shift the cosine of different frequencies in a certain way. When you add them up, you end up with this periodic signal. And that's the importance of phase. Now, this is the same signal. We found A0. We did it earlier. We found AN, BN. If I want to find the compact C0, it's just going to be exactly like the A0. We're going to use these properties. We're going to use this property to find C0, Cn, theta n. So C0 will be the same as DC. Cn will be the square root of an plus bn. You square these, you add them up, you get this. Theta n is tan inverse minus tan inverse bn over an, or tan inverse minus bn, same thing. If you plug bn, this quantity, and divide it by an, this quantity, you should get this one. And the compact will be the DC, C0, that's C0 here. Cn is this quantity times the 0.504, and theta n is this quantity, and that's the compact. With the compact form, we can plot the line spectra of the signal f of t, or if we call it x of t. Line spectra, I mean you plot the amplitude of each harmonic. Basically, you plot these for n0, n1, n2, n3, and so forth, that show you the strength of the different harmonic. Also, you plot the phase, theta n versus n, or versus omega. And this we call it the line spectra. And if we do this one for this signal, if I plot C0, that will be here. If I plot the first harmonic when n is 1, so I plug for n1 here, and I should get this value. Here in the x-axis, you can plot omega, or you can label it as n, the harmonic. So this is the first harmonic. We found omega, remember omega 0 was 2, the fundamental frequency. So that's the first harmonic, or the fundamental frequency, 2. That's the second harmonic, 2 times 2, 4. Third harmonic, 3 times 2, 6, and fourth. Fourth harmonic, 4 times 2 is 8. And if I plug for n1, I get this value. If I plug for n2, second harmonic, I get this value, n3, and so forth. And when you look at this plot, you will see as the frequency increases, the amplitude decrease. Now, for speech compression or signal compression, as I can see, the fifth harmonic become very small, sixth harmonic even smaller and smaller and smaller. I can ignore them, and I will only save these harmonics and transmit this harmonic. And if I want to reconstruct this signal back again, I will use only these harmonics. So I'm going to use from n1 until n4. I don't have to go to infinity. And if I plot it, it would be very close to here, except maybe at the top here, you may find something like this, because this edge, the high frequency make them, and I'm deleting the high frequency component. And that's one application, is how do you decide how much compression you do, how much high frequency you get rid of. In a telephone, human speech can have a frequency from 20 hertz all the way to 20,000 hertz, but they delete all frequency above 4,000 hertz. And if they transmit the frequency component up to 4,000 for human speech, you will hear the speaker and what is he or she trying to say clearly. Speech recognition will be perfect. Let's continue. Now we will do the exponential form. The advantage of exponential form is very easy to calculate. You don't have to calculate A0, AN, BN to find Cn and C0 and theta n. No. In exponential form, a signal can be represented as a linear sum of dn amplitude, and dn usually complex, so it will have magnitude and phase and exponential. And n will go from minus infinity to infinity. If I add all these, I can represent a periodic signal. In this representation, all you have to calculate is dn. That's it. And that's why it's very attractive, the exponential form, to calculate dn. So now how are we going to calculate dn? We can multiply this by e minus j2 pi f0 mt and multiply this also by the same thing, e minus j2 pi f0 mt, and then integrate over a full period and integrate over a full period. When you multiply these, if n does not equal m, you will always get 0. The only time the integral will give you a value if n equal m. In this case, when m equal n or n equal m, these will cancel, you get 0, and the integral will be just dn dt over a full period. And if I integrate this one, this will be dn t0. And this quantity here will be just this quantity. This is this here. And this summation here with the integral, you get dn t0. If I divide dn by t0 and divide here by t0, I get this. And dn will be the integral of this one divided by t0. t0, this one. And that is how you find dn. You find dn, you take the periodic signal x of t, you multiply it by this exponential, and you integrate over a full period, and you average it. You divide by t0, and you find dn. And most of the time, dn will be complex value. For example, d1 could be 3 plus j4. Then d minus 1 will be the conjugate of these, 3 minus j4. Why? Because if I go here, if I add d1 and d minus 1, they have to be conjugate. So when you sum them up, you get a real signal. Because remember, x of t is a real signal. So it's always going to be the true. d2 and d minus 2 will be also conjugate of each other. That means the magnitude will be the same. So that's always true. The magnitude of d positive n and negative n, the magnitude will be the same. And the phase will be negative of each other. So if I find the phase of this one, it's tan inverse the imaginary 4 divided by the real, and this will be tan inverse the imaginary minus 4 divided by the real. The phase are theta minus 1 equal minus theta 1. So this is always true. We say the phase odd, the magnitude even, and always this conjugate of each other. If that's not the case, then you made a mistake somewhere. And to plot the line spectra, and here is why d minus 1 has to be, and d1 has to be conjugate of each other. Try to do this summation. Sum these and sum these. You will end up with a cosine function, a real signal. Sum this one and sum these. If these two are conjugate, then you will end up with a cosine function, which is this one. So this term will give you this one, these two. This term plus this term will give you this. And that will only be true if d minus 2 and d2 are conjugate of each other, d minus 1 and d1 are conjugate of each other. The d0 is the c0. So this is the relationship between the exponential Fourier series coefficient and the compact trigonometric Fourier series coefficient. This is the relationship. This is theta n. We called it before. I will stop here for this lecture, and the next lecture we will carry out these examples.